Welcome back, fellow mitochondriacs, for another episode of Cancer is a Mitochondrial Metabolic Disease. So, we have now hit two major kind of action steps within the glycolysis system. We've hit the glucose transporters and we've hit the hexokinase enzyme. And we're going to be systemically kind of trying to dismantle aerobic glycolysis or the Warburg effect, one enzyme at a time. And the next enzyme that we're going to be talking about is an enzyme called phosphofructokinase. And in the, I guess, investigative part of my work behind the scenes, I have been able to come up with a lot of important kind of pieces of information that I was previously unaware of. And I was able to come up with quite a few things that have inhibitory action on this enzyme. And you're going to see that that's going to be very important going forward. And so without further ado, let's get into it. Okay. So phosphofructokinase is a very key enzyme and step within glycolysis, and it's going to be referred to throughout this entire video, as PFK. And we'll talk about the different isoenzymes that there are in a variety of cancers. But just to give ourselves a kind of figuring out where we're at right now, as I discussed at the very beginning, we've hit the glucose transporters already. We just finished, when talking about 3-bromopyruvate, talking about hexokinase. And we're now going down a step to talk about phosphofructokinase. And phosphofructokinase is kind of a lot more important than I thought it was when I was initially going through this literature, just because it wasn't quite as robustly, I guess, available in the literature in terms of the amount of papers and the amount of things that have been studied to inhibit it. But the more I got into it, the more I realized that it's really an important topic for us to discuss, especially within this context of looking at cancer from a metabolic perspective. So the first paper that I pulled was published in December of 2023, and it's titled "Hitting the Sweet Spot: How Glucose Metabolism is Orchestrated in Time and Space by Phosphofructokinase 1." And it says here that glycolysis is a central metabolic pathway across all kingdoms of life. Intensive research efforts have been devoted to understanding the tightly orchestrated process of converting glucose into energy in health and disease. Our review highlights the advances in knowledge of our metabolic and gene networks are integrated through the precise spatiotemporal compartmentalization of rate-limiting enzymes. We provide an overview of technically innovative approaches that have been applied to the study of phosphofructokinase 1, PFK1, which represents a fate-determining step in the oxidative glucose metabolism. And later in the paper, it says, metabolic reprogramming is a classic hallmark of cancer. Most notably, cancerous cells exhibit an increased rate of glycolysis independent of the amount of oxygen present. This phenomenon, known as aerobic glycolysis or the Warburg effect, is thought to create a metabolic environment that supports high levels of cellular proliferation through accumulation of nutrients and free energy. It is not surprising that PFK1 expression is also increased in many cancers, seeing as it is one of the key enzymes that determines glycolytic rate, as has been previously shown that increasing PFK1 expression promotes, I'm going to highlight this, promotes aerobic glycolysis or the Warburg effect, directly connecting PFK expression with the metabolic phenotype seen in cancer. PFK1 expression increases in breast cancer, lung cancer, brain cancer, bladder cancer, and colon cancer. Likely all cancers, given that all cancer is using the Warburg effect, but I think they're just trying to highlight that it's very upregulated in those particular cancers. This increase in PFK1 expression is not observed across all isoforms equally, with L and P being the most predominant isoforms in cancer. Tumors and increase the so it later said tumors and increases the expression of PFKL, and you'll see that means liver type, to promote glycolysis. Additionally, the activation of hypoxia factor pathway, which commonly promotes tumor growth, has been tied to increased PFK1 activity through allosteric activation, typically fructose 2,6 biphosphonate. So what I wanted to highlight in this particular part of it is that it's, number one, it is a very, very important enzyme for glycolysis, number one. Number two, it actually will help determine the rate of glycolysis that is happening, and that increasing the expression of PFK will actually promote further kind of like the vicious cycle of the Warburg effect. And it's seen in several, very common cancers: brain, lung, bladder, breast, and colon. And then not lastly, but next, it's highly under the control of the hypoxia-inducible factor pathway, which we've talked about at length, being activated by either true hypoxia or pseudohypoxia. And then the next thing it says here is that a lack of a PFK enzyme results in the inability to break down glucose and leads to skeletal muscle deterioration and indirect kidney damage. Together, the altered functions of glucose metabolism that result from genetic mutations of PFK highlight the fundamental importance of regulating tight regulation of the activities. So I put this in here because, I would say that it just goes to show that, like, probably one of the strategies that would not be of maximal benefit, as we looked at with glucose transporters and hexokinase inhibition, is not being keto adapted first. Because when you are relying on glucose, some tissues more than others, and you were to completely remove the enzyme, that's what they did. They removed the enzyme completely. It led to, breakdown of muscle and even kidney damage, probably from the breakdown of muscle indirectly, it says. So I'm guessing maybe that, the creatine kinase that's released from muscle or whatnot, or the LDH potentially damaged the kidneys. But my point is that being on a ketogenic diet first is so critical, because as we saw in the previous videos about hexokinase, it actually was theorized and likely does mitigate any of that damage and kind of minimize the damage at minimum. Just want to put that in there. And then it last says here that PFK1 expression has been tied to cancer in numerous ways. The most obvious being to promote glycolysis and cancerous growth. And I just wanted to, put that in writing, that this is not just me saying that. This is like been clearly connected between cancer, its growth, Warburg metabolism, and the amount of phosphofructokinase, or PFK, that's being expressed. It later says that in the 1980s, F26BP was identified as a novel regulator of PFK, now known as PFK's most potent activator. F26BP increases PFK activity while relieving ATP inhibition, while increases glucose uptake and metabolic flux. And it says later that there are, again, PFKB isoforms. And this is what actually probably the next video will be on. This was a part of metabolism that I frankly had no idea about. And because I was looking at things that could either increase the activity or decrease the activity of this particular enzyme, PFK. And that's where this other enzyme that is not part of glycolysis, but is kind of very tightly related to glycolysis, this PFK FB enzyme was kind of talked about in this paper and in other papers. And I found that it was pretty darn important because it is responsible for regulating this F26BP, another metabolite that has strong regulatory capacity over PFK. And I wanted to, I think that it's definitely worth probably doing a video on, since we're, systematically trying to truly dismantle Warburg metabolism. Later, it says that PFKB is an essential determinant in the regulation of carbohydrate metabolism by controlling the concentration of 2F26BP in cells, which is the most potent activator of PFK activity. Therefore, its altered expression in certain cancers can lead to aberrant glucose metabolism. So again, I'm not going to dive too deep into PFK FB because, to be very frank, I haven't done my own deep dive about it yet. But it seems to be pretty important. And so if there are known inhibitors of the PFK FB as well that I want to get into at a very near future date. But for now, I'm just going to highlight that there is activity by that enzyme and its product of that enzyme that has high regulatory effects on PFK. And I just want to skip down to this particular slide because it kind of highlights what we're talking about. So we have glucose hexokinase. Here's phosphofructokinase 1, right? We're talking about this enzyme in this video. And we see here that it's downregulated. This is like normal physiology, maybe not really related to cancer. And it's kind of like pathological metabolism. But we see here that it's downregulated by ATP. So we have feedback mechanisms, right? We have feedback. If we have enough energy, then we don't need as much glycolysis. So ATP, citrate, even hydrogen protons can inhibit it, whereas AMP and this fructose 2,6-biphosphate, the F2BP, the chemical that I was just referring to in that last slide, also has it's actually said that it's the strongest activator of this. And we'll see kind of how that flows in the next coming videos. And then this was the next slide after that last one. So this is just another picture of how glycolysis looks and the offshoot pathway. So here's the PFK FB where it relates to phosphofructokinase and how it gets created into this fructose 2,6-biphosphate, which is a potent activator of PFK. What it says here for future perspectives, it says that metabolism changes as a cancer develops from a small pre-malignant lesion to an aggressive primary tumor and then metastasizes. Overall, PFK activity is closely tied to cancer, particularly cancers of female reproductive system. Additionally, the downregulation of PFK in cancer has also been shown to be advantageous for creating more metabolite availability for other biosynthetic pathways. Knowledge of how PFK is fundamentally regulated and how this regulation goes awry in cancers will provide insight into understanding context-dependent metabolic fluidity. Both the upregulation and downregulation of PFK can promote cancer cell growth. So why would they say that? Well, just going back to our slide here, remember, glucose 6-phosphate is what is used to is the first step in the PPP. So the PPP, or the pentose phosphate pathway, is used to make other things like nucleotides, RNA, DNA. It helps recycle glutathione, etc. And so therefore, if we were to completely shut down PFK without addressing the upstream, lowering blood glucose, lowering glucose getting into the cells through glucose transporters and blocking hexokinase, and even maybe blocking glucose 6-phosphate dehydrogenase or G6PD, then maybe only looking at blocking phosphofructokinase would not be, it's not that it wouldn't be fruitful, it just wouldn't be as fruitful maybe as we think, because glucose is still being brought into the cell at a high rate if you're not addressing the other pieces as well. And glucose 6-phosphate would be then shunted into the PPP to make DNA, RNA, and protect the cancer cells from oxidative stress via glutathione kind of recycling, and kind of recycling of multiple antioxidant systems like the thyrodoxine system, like we talked about in the last video. So my point is that although PFK is a critical step in allowing the Warburg metabolism and glycolysis to continue on to make pyruvate and subsequently lactate and shutting down the energy production from cancer cells, it's just that as of most things we've talked about so far, it would probably not want to be the first line treatment or done in a vacuum, because it may have unintended consequences that we would be potentially facing. Let's see here. So it says knowledge of how PFK is fundamentally regulated on this and how this regulation goes awry in cancers provides insight and understanding. Okay, we talked about that. For instance, optogenetics provide exquisite spatial resolution and fast reversibility to acutely and dynamically dissect a metabolic pathway's action. And overall, the enzymatic activity of PFK1 is tightly orchestrated across cell types and tissues through multiple spatial temporal mechanisms. While many controlled processes are dedicated to tuning PFK1 activity, how these regulatory principles contribute to metabolic stages and tumor types are still beginning to unfold. PFK is an irreversible, essential component of glycolysis, which suggests that interventions aimed at PFK1 could offer an important vulnerability for disrupting glycolytic-driven cancer cell metabolism. Furthermore, all three mammalian PFK1 isoforms generate FBP. However, the unique, highly specific regulation of each isoform suggests that moonlighting functions of PFK1 may also contribute to the process of cancer and have yet to be uncovered. As organisms became more complex during evolution, cells may have devised subcellular localizations as a dynamic mechanism to provide tighter regulation of cellular processes. Thus, the cell may have evolved such approaches in order to compensate the irreversibility of PFK1 activity. So I think what we can get from this initial kind of look at PFK in this paper is that it is a critical step in glycolysis. The upregulation is seen in a variety of cancers, and that provides the energy through the Warburg effect and aerobic glycolysis, substrate level phosphorylation, as talked about by Siegfried and his group. But its upregulation and downregulation could be problematic in a vacuum, because if we shut it down completely without addressing the other things, we could create some unintended consequences. And they basically think that PFK has kind of moonlighting ability to potentially convert other substrates, and they haven't quite uncovered that yet. So this paper, pretty recent, August 2024, says phosphofructokinase 1 in cancer, a promising target for diagnosis. We'll also see that there's probably a promising prognostic ability as well as for therapy. And it says tumor cells have distorted enzymatic houses, which change the metabolic state from oxidative phosphorylation or OXPHOS or mitochondrial energy production to glycolysis with high lactate levels in a hypoxic or low oxygen environment. Redrafting the metabolic profile is an emerging hallmark of cancer. Glycolytic enzyme amplification occurs in about 70% of malignancies. currently studies have found that PFK1 overexpression is linked to cell migration, proliferation, and overall survival rate in various human cancer cell lines. This review intended to uncover the bona fide therapeutic target for cancer therapy and elucidate the role of PFK1 in cancer. Furthermore, with this review, we have outlined the listed pharmacological and genetic inhibitors of PFK1. In a variety of malignancies, inhibition of expression of PFK1 isoforms has been reported to be the most effective therapeutic method. Overexpression of PFK1 isoforms induces the Warburg effect, cell proliferation, and carcinogenesis by downregulating apoptotic proteins such as caspase 3, 9, 8, YY1, synoviolin, shRNA 507, SNAI, MIR. I'm gonna skip reading all these because it's not really helpful for us. Are some of the putative genetic inhibitors against PFK1 that have been used to manage the development of malignancies. Pharmacologic inhibitors such as penferdol, synoviolin, HRD1, quercetin, genocinoside 20S-RG3, triptolide, wolnerine, salicylic acid can be regulate the advancement of malignancies by inhibiting PFK1. Thus, PFK1 is a promising molecular biomarker for cancer treatment. And I'm going to talk about a lot of these inhibitors here in the next coming slides, but I wanted to first continue talking about its role in cancer growth, but also to see its regulation by other systems that have that are potential targets for us for treating cancers and metabolic disease. So before I get into this slide, I'm gonna read this paper that was published in 2023. It says PFK is highly expressed in certain types of cancer, such as lung, breast, T and B cell leukemia, and ascites tumor. Don't know what that is. Importantly, data analysis of the Human Protein Atlas shows that PFK-P type, that's platelet type, expression is negatively associated with overall survival in cervical cancer, head and neck cancer, liver cancer, lung cancer, pancreatic cancer, renal cancer, urothelial or bladder, or the cancer that affects the tubes that go from the bladder to the kidneys, the ureters. So basically, if there is increased expression of PFK, this platelet type, it's associated with survival, inversely associated with survival. So the higher the expression of PFKP, the lower the survival is in cervical cancer, head and neck, liver, lung, pancreatic, renal, and urothelial cancers, suggesting that PFKP may be used as a prognostic purposes in cancer. And we talked about this already, the kind of the inhibitors and so on and so forth. So I'm going to put this up here. But some of the things that are not talked about so far, which I thought was of critical importance for us, was found in the next couple of slides and papers, but this one most piqued my interest. It was published in July of 2018. It says, insulin specificity, specifically regulates expression of liver and muscle phosphofructokinase isoforms. So it says phosphofructokinase is a key regulatory enzyme in glycolysis. We've talked about that now, being considered the pacemaker of the pathway. In mammals, this enzyme exists in three isoforms: PFKM or muscle, PFKL liver, and PFKP platelet, presenting different regulatory and catalytic properties. And it says here, our results revealed that the lack of insulin significantly impacted the expression of PFKL, presenting mild effects on PFKM and no effects on PFKP. The decrease in PFKL and mRNA levels observed on the treatment group with STZ was reversed by the treatment with insulin. In conclusion, insulin, the most potent known regulator of glucose consumption, specifically regulates the expression of PFKL and PFKM, which impact the regulation of glycolysis in the cell. So the reason I wanted to particularly highlight this paper, this text, and this slide, or this graphic, is because something that I read really early when trying to study Seyfried's work and ketogenic metabolic therapy for cancer, and what they said, and I don't remember what paper it was. I could probably pull it somewhat quickly, but what really struck me was that they believed that the ketogenic diet was effective for kind of three major reasons. Now, my first thought, by learning about all of this at the beginning, thought, well, yeah, it's ketogenic diet, it's low glucose. The reason it's most effective is because it has low glucose, and that's going to lead to lower blood glucose. And although that's a key reason for the ketogenic diet, I was surprised by the text from the authors, and it said that they thought that the reason the ketogenic diet was so effective, actually, the most important reason, was lowering insulin and raising ketones. And I was very surprised by that. And I think this and other things we've seen so far while looking at this, mega series on cancer's metabolic, disease, is that insulin is very important at doing a lot of things. And as we can see here, insulin has a potent effect at upregulating not just PFK, but multiple enzymatic steps within glycolysis. And in particular, it has effects on this PFKL or liver type and PFKM muscle type. But it doesn't have any effect on PFKP platelet type. And you may say that, well, the last paper we looked at, it was looking at PFKP as being highly expressed in certain types of cancer, right? So why do we care? And I would say that, as you'll see, most of the isoenzymes or the types of PFK are expressed in a variety of cancers. And so therefore, even though this particular subtype, the one type that doesn't have response to lowering insulin, it doesn't mean that lowering insulin still isn't important. And especially for these other types, which are seen in a variety of cancers. And I just wanted to highlight that. The next thing I wanted to highlight was us talking about a pathway that we have really not talked about in a video on its own, and it probably deserves its own video because it is such an important pro-growth pathway, and that is the PIK3 AKT mTOR pathway. And we're going to talk about not only the pathway itself, but also things that can inhibit that pathway in the, I wouldn't say like remote distant, but it will be fairly distant because we still got to cover a lot of things within glycolysis, within fatty acid synthesis, within, I may even want to cover, oxidative stressors, just because I think that that's an important thing for us. But it'll probably be definitely before the medicinal mushrooms, which I have tons to share about medicinal mushrooms. My point is that it's something that we have probably touched on in dozens of videos. It's just that we've never actually had a specific video about it. And I do want to touch on, I do want to have a specific video on it. And I definitely want to talk about things that inhibit the PIK AKT mTOR pathway. But that being said, I do think that there's definitely a role here talking about it, at least kind of in a very specific way, when it relates to phosphofructokinase. And it says here that PIK3 AKT is one of the most frequently altered signaling pathways in human cancers, supporting the activation of many proteins sustaining metabolism, proliferation, and aggressiveness. Another important frequently altered Another important pathway frequently altered in cancer cells is one regulating this YAP-TAZ transcriptional co-activators, which promotes the expression of genes sustaining aerobic glycolysis, such as the WNT, MYC, HIF1, EMT, and drug resistance. It later says that here we want to highlight how the glycolytic enzyme PFK1 and its product P16BP promotes the activation of both PIK3 and AKT and YAP-TAZ pathways by several distinct and indirect mechanisms. In turn, PIK3, AKT, YAP-TAZ can promote PFK activity and fructose 1,6-biphosphate production in a positive feedback loop, thus sustaining the Warburg effect in drug resistance. Thus, we propose that the inhibition of PFK and its key activator, PFKB, which we'll have a whole video on, could potentiate the sensitivity of PI3K and YAP inhibitors currently tested. Awaiting the development of non-toxic inhibitors of these enzymes, we propose to test the administration of citrate at high dosages because citrate is a physiologic inhibitor of both PFK1, PFK2, PFK-FB3. Consistently, in various cultured cancer cells, including melanoma, sarcoma, hematologic malignancies, and epithelial cancers, this citrate strategy efficiently inhibits the IGFR1 AKT pathway, promotes PTEN activity, reduces BCL, XL, MC1 expression, and increases sensitivity to standard chemotherapy. It also inhibits the development of sarcoma, pancreatic, mammary, HER2 positive, and lung RAS-driven tumors in mice without apparent toxicities. So this is a lot, okay? A lot. So before I get into this very busy slide, looking at the PIK3 mTOR pathways and how it kind of relates to cancer and how it relates to importantly to this video, PFK. Let me unpack something that I thought was of critical importance that we discuss. So sometimes I personally am very surprised by things that I find in the medical literature. And one of the things that I'm surprised by is how something that seems like it could be very bad and still could be bad, okay, could have a beneficial effect somewhere else. And in this paper, I was shocked by the effect that citrate, or the citrate strategy they refer to here. Now, going back to this slide here, we see that citrate is an inhibitor of phosphofructokinase under normal physiologic conditions. And that somewhat makes sense because citrate is part of the citric acid cycle or the TCA cycle. And you would imagine that if citrate is building up, it means that there's abundant amounts of energy. So therefore, it would probably shut down glycolysis at least at some level. And since they're considering phosphofructokinase the pacemaker of glycolysis, it seems like it would be important to block, probably hexokinase or phosphofructokinase with citrate. And, for example, I'm going to skip way down in a way that I wasn't expecting. But there are strategies within metabolic therapy where they are using citrate inhibitors, or let's see if I can find the correct, slides, and we'll have a video on this. But as you can imagine, I have a lot of slides here. Wow. I think it's this slide here. Here it is. So we're going to have a video on this, and we'll talk about things that can do this. But citrate is critical for de novo lipogenesis, okay? Making the new fatty acids from glutamine, actually.
Glutamine is what will turn into citrate, and citrate will help make fatty acid synthesis. And so my point is that, I've talked about this on videos, but I've also, answered probably dozens of comments talking about the types of magnesium you should take or whatnot. And my impression is that knowing this metabolism here, it seemed like giving citrate would be a pretty darn bad idea. Okay. So, magnesium citrate, potassium citrate, whatever, would not be a fantastic idea, because it would probably likely lead to increased availability of citrate available to the cells, which would be converted to new fatty acids through this pathway here, and potentially lead to problems for us going forward, and basically feeding cancer in some way, not in the traditional sense that we talk about with glucose and glutamine, feeding cancer to make energy, but more feeding cancer to give it substrate or raw materials to create new fatty acids, right? So I was very, very guarded when talking about citrate and its potential either harms by giving it as a supplement. But this paper here, talking about citrate metabolism, and just trying to reorient here, seeing that citrate has a deleterious effect and an inhibitory effect on phosphofructokinase, and how this group here used this citrate strategy, like they mega dose citrate, right? Again, this was in culture and in mice, but when they gave citrate, it effectively inhibited not only PFK, but it inhibited this whole entire AKT pathway, which has downstream, beneficial effects. And it made cancer more sensitive to chemotherapies. And it also inhibited the development of sarcomas, pancreatic cancers, breast cancers that were HER2 positive, lung cancers that were RAS driven, without any apparent toxicities to the normal cells. So it just goes to show that we all have a lot to learn. And I still think, even after reading this paper or this abstract here, that I would not want to be giving people citrate in large amounts at this point. But it's possible that there could be a paradoxical beneficial effect that is elicited by the use of citrate. And I just wanted to highlight that kind of paradox in the literature here that leaves me, at least, scratching my head a little bit about what to do about that. But I'm going to get back on track talking about PFK and look at this slide here. So this slide was part of this paper, and it's a beautiful slide, but it's a very busy slide. And I think, number one, it highlights the complexity that we're dealing with, right? And we're seeing here that glucose is being brought in by this glucose transporters, right? It's being converted to fructose 6-phosphate by a variety of enzymes, but hexokinase. And then it's going to get converted to the next step, which is fructose 1,6-biphosphate from PFK. Okay, here's PFK1. We're seeing here that citrate has the inhibitory effect on both PFK1 as well as PFK-FB, which we'll have a whole video on. And that having a beneficial effect. We also see that citrate here is being used to make lipid synthesis and other things, which we know could be potentially harmful, new nucleotides. So it's not all rosy there, okay? But what we're seeing here is that stress receptors, that IGF-1 or insulin-like growth factor 1, EGFR, all of these signaling cascades will work to upregulate this PIK3 AKT mTOR pathway, which has a variety of kind of bad things that it does within cancer. Number one, it changes genetic, expression. It will upregulate, glucose transporters and PFK2 and PFK1 isoenzymes. It will strongly upregulate PDK, similar to that of hypoxia-inducible factors, which will then basically block pyruvate from getting into the mitochondria. So therefore, it has to go to lactate and kind of feed forward the Warburg effect. So we see here that it's a very complex system here. And, this paper highlights kind of the importance of PIK3-AKT pathway for glucose metabolism. And this paper is titled "A Dangerous Liaison in Cancer." And it says here that aberrant activities of PIK3-AKT pathway commonly occur in cancers and correlates with multiple aspects of malignant progression. In particular, recent evidence suggests that PI3K-AKT signaling pathways plays a fundamental role in promoting the so-called aerobic glycolysis or Warburg effect by phosphorylating different nutrient transporters and metabolic enzymes such as GLUT1, hexokinase, PFK, B3 and 4, PKM2, by regulating various molecular networks and proteins, including mTOR, GSK, FOXO, MYC, and HIF1 alpha. This leads to profound metabolic reprogramming of cell metabolism and also impacting on the pentose phosphate pathway, mitochondrial oxidative phosphorylation, de novo lipid synthesis, and redox homeostasis, and therefore allowing the fulfillment of both catalytic and anabolic demands of tumor cells. So the graphics of this paper were not fantastic. They're very small. And so therefore, when I blew them up, we see that it gets a little bit blurry, I guess I would say. But we see here that all of these, the enzyme, the pathway is having effects on glucose transporters. It's having effect on G6PD. It's having effects on hexokinase, phosphofructokinase, FB, as well as other. So my point is that this is going to be an important kind of indirect target to affecting aerobic glycolysis in multiple steps. Okay, but obviously we're talking about it and its effects on phosphofructokinase 1, which is the purpose of this particular talk. And obviously we can get into the weeds here with PFK signaling, but it's important for lipid synthesis, changing oxidative metabolism, glucose metabolism, pentose phosphate pathway, and redox homeostasis. I will say that this is a little bit misleading. It makes it seem like it's improving mitochondrial function or something like that. Actually, it's doing the exact opposite. Just looking at this graphic here, when PIK3-AKT is activated, it will upregulate PDK, which will effectively shut down mitochondrial energy flux. So even though this arrow makes it look like it's having a positive effect on energy metabolism through mitochondria, that's actually not the case. And it will basically enhance growth, metastases, and drug resistance. So it is an important pathway. And the fact that it, has a direct effect on phosphofructokinase, which we're talking about in this video, as well as other key glycolytic steps, means that this is going to have to be something we talk about big time as a way to have an effects on this in the future. I only showed this particular slide not because we're going to talk about all of these different pathways, but I just want to show the complexity of what we're dealing with here. We have a variety of pro-growth, mechanisms. This WNT beta-catenin pathway. We have the YAP and TAZ pathway we just talked about, which kind of signals through c-MYC. We have the PIK3-AKT mTOR pathways, which work synergistically with MYC as well as hypoxia factors. And you can see here that they have effects on the glucose enzymes, glucose metabolism from a variety of different mechanisms. We also see how the inflammation here through NF-kappa B and a variety of kind of pro-inflammatory cytokines also will have effects on glucose metabolism also, which in this case, we're talking about the progression of osteosarcoma, a very kind of nasty bone cancer. But my point is that there are a variety of influences that are affecting glucose metabolism that are upregulating all of the key enzymes, such as phosphofructokinase. And those are going to have to be addressed via diet and potential supplementation and medications. And we will talk about those at a later date. Some of these pathways like the WNT beta catenin, or let's say MYC or RAS, or let's see here, MAPK or EGFRs, or all these other things. These are things you're going to hear in conventional oncology because they're trying to do either a monoclonal antibody or some drug to inhibit those pathways. But you can see here, just from the complexity of this, obviously, if you're, I don't know, let's say, where was it at? We see here that EGFR, let's say your cancer has, somebody told you your cancer is EGFR. Well, EGFR is just one way that PIK3 is upregulated, right? RAS, here's RAS. Maybe you have a RAS-driven tumor, right? RAS is just one way that PIK3 AKT is upregulated, right? And so my point is that when we are playing the game that kind of conventional medicine is doing by blocking RAS, okay, yes, we've had an effect on PI3K mTOR pathway from one particular perspective, RAS or MYC or EGFR. We are missing all these other pathways that are likely being affecting, glucose metabolism. And then it also makes you wonder, like, we're worried about RAS, we're worried about EGFR. What is it effectively doing? It's effectively upregulating glucose metabolism, which transforms the Warburg, or forward feeds the Warburg effect, right? So it all goes back to metabolism. If it doesn't matter if your cancer is osteosarcoma or a breast cancer or a glioblastoma multiforme, it all needs gasoline to run that cancer. And that gasoline for cancer is glucose and glutamine. So therefore, you can see that all these pathways that people are being told about, they all relate to glucose and glutamine because that's what keeps the engine running. And it's a little bit frustrating because I think that we make EGFR, or we make, some of these like aberrant pathways the big thing, when the big thing is clearly aerobic glycolysis, and where cancer gets its fuel by the pressing of the gas of RAS or PIK3 or EGFR, right? That's just pressing the gas. But if there's no gas to run it, there's no glucose or glutamine, it doesn't matter how fast or how hard you're pushing on that gas pedal. Took a little aside there, but it was critical for me to kind of vent my frustration, I guess, with you all, because people get focused on, I would say, the wrong thing. So the next paper that we're going to be talking about was published in January of 2016, and it says here that the PFKL MIR 128 axis regulates glycolysis by inhibiting AKT phosphorylation and predicts poor survival in lung cancer. And I'm not going to really go over the paper. I just wanted to kind of show that, unlike, what was it? This, I think it was, where was it? This was it. This was PFKP, right? It showed a poor prognosis and survivability in a variety of cancers. And just like PFKP, PFKL also predicts poor survivability in a variety of cancers. This is a lung cancer model for, let me see if it gives a specific lung cancer model. I don't think it just says lung cancer. It doesn't say which type. And then another poor prognostic potential of PFKP. So PFKL, PFKP, PFKP again, can all be kind of prognostic, tests that you could potentially use in the future to kind of explain like how aggressive and how reliant on glucose your cancer cell type is, right? And I'm not going to read this, but it says phosphofructokinase platelet type, overexpression, accelerated colon cancer cell growth and motility. And, we see here that in normal cells, you have a normal amount of PFKP or even a low amount. Obviously, that's a relative amount. And then a colorectal cancer cell model, you're going to have high amounts of PFKP. And when you give high amounts of glucose with high amounts of machinery to deal with that glucose, obviously you're going to have, cell growth. So although we're specifically talking about PFK in this particular paper, let's not be naive and think that, it's only PFK that is upregulated in these colorectal cancer cell models or in these liver cancer models, or lung cancer models, et cetera. It's going to be the entirety of glucose metabolism. We're just happened to highlight PFK in this particular video. The next paper that I wanted to go over was published, 11 years ago, March of 2014. And I particularly got this because it said things that were so insightful. Again, this is not a Dr. Seyfried paper. This is not, an echo chamber. But this was so insightful, even 11 years ago. It was pretty apparent to a lot of authors that the way that conventional oncology was dealing with this problem is not the way to do it, or at least it's not the first line way to do it, right? So it says here that nearly a century ago, Otto Warburg made an astute observation that the metabolic properties of cancer cells differed markedly from those of normal cells. Several decades passed before the concept of exploring cancer cell metabolism came into clinical practice with the advent of chemotherapy, the underlying principle of which is targeting rapidly dividing cells by interfering with critical processes that are at some level driven by cell metabolism. Although chemotherapy can be quite effective, success rates are highly variable, and the adverse effects associated with treatment often outweigh the benefits due to the fact that chemotherapy is indiscriminately cytotoxic against all rapidly dividing cells, cancerous or healthy, which is why your gut gets tore up, which is why your hair falls out, which is why your liver gets damaged, because these rapidly dividing cells are getting killed at the same time as the cancer cells. And as we've seen how cancer functionally works with creating a metabolic shield with lactic acid around it that inhibits chemotherapy from getting to where it goes by creating an internal metabolic shield with glutathione and other antioxidant systems, the cancer cells are actually more protected than the normal cells from chemotherapy. During the past several years, a more intricate understanding of cancer cell metabolism has permitted the development of targeted therapies that aim to specifically target cancer cells and spare healthy tissue by exploiting the ultrametabolism of cancer cells. The identification of new metabolic targets and subsequent development of small molecule inhibitors of metabolic enzymes have demonstrated the utility and promise of targeting cancer's cell metabolism as an anti-cancer strategy. This review summarizes recent advances in identification and characterization of multiple metabolic enzymes as emerging anti-cancer targets. It later says in this paper, although chemotherapeutic agents can be quite effective, success rates are highly variable, as it says in the abstract. Moreover, the adverse effects associated with chemotherapy often outweigh the benefits. Current regimens can be highly aggressive and are associated with extremely adverse side effects that severely affect quality of life. Because chemotherapeutic agents are indiscriminately cytotoxic, they prove to be equally detrimental, if not more detrimental, let's be honest, to all rapidly proliferating cells, whether healthy or cancerous. Common side effects of chemotherapy result from the damage incurred by rapidly proliferating healthy cells, including alopecia, your hair falling out, due to effects on hair follicles, myelosuppression, or crashing of your immune cells, and nausea, vomiting due to gastric mucosa. Life-threatening side effects include vital organ toxicity and secondary cancers that are caused by the very treatment that we give. So again, I highlighted this because 11 years ago, these authors were obviously right on track, knowing that what we're doing is not in the best interest of patients. It is, maybe you could argue that it's in the best interest of patients 100 years ago, when we have no idea about cancer's metabolism, about the Warburg effect, etc. And I would just say that now we're at a place, because again, we're 11 years after this paper was published, talking about the elephant in the room, right? I don't believe, sadly, that the change is going to come from inside medicine, because, and I think we're all guilty of this to some degree or another, but it's really hard to change a paradigm, and the literature is changing the paradigm behind the scenes, but it's not being changed in clinical practice in any way, shape, or form. I mean, we still have doctors and oncologists nowadays saying that your diet and glucose has nothing to do with cancer. I mean, could there be a more false, misleading, and harmful statement to a cancer patient? And that's where we're at, right? In the state of affairs in April 25th, 2025. So I do believe that we have ample evidence that the metabolic approach to cancer is, as of now, it seems to be the best way to attack this problem. I would say that prevention is a more powerful strategy, which is a completely different strategy. But from a therapeutic perspective, like once a person is diagnosed with cancer, metabolic therapies make the by far most sense, and it likely is the safest, and is likely the most effective, and is likely going to lead to the least amount of side effects. And being honest, it's going to be probably the cheapest also, because we're talking about like substances that were not patented or can't be patented. We're talking about vitamins, we're talking about minerals, we're talking about phytonutrients, we're talking about dietary changes, we're talking about exercise, we're talking about cold plunging, we're talking about things that really can't be patented, and are going to be easily accessible to most humans, and are going to be cheap. So the paradigm is changing. It's just that it's not going to come from within. It's not like, I don't believe oncologists one of these days are going to be like, oh, well, now we get it, and we're going to recommend ketogenic diets and everything's going to change. I think that it's going to have to come from patients, families who are affected or afflicted by cancer or whatnot, and it's going to have to come from the outside. And we're going to probably have to create like a parallel system that allows for this, and where money talks, basically. People who are enlightened about this treatment mechanism will flock, God willing, not flock, because that means there's lots of people with cancer, but you know what I'm saying. We'll go towards the treatment modality that is cheaper, that is safer, that makes more sense biologically, that there's evidence to suggest that is the best way to handle it. And they're going to go that way, and people are not going to spend their dollars on the conventional treatments. What I'd also say is that there also needs to be like almost a alternative cancer insurance program, because one of the reasons why people are kind of forced into the system is because the standard of care is covered by insurance, and being on a ketogenic diet, doing IV vitamin C and HBOT is not covered by insurance. So it kind of like selects out the like rich people, or the well-off people, or the people who are willing to kind of like sell everything they own, which is really a sad situation. So, we need to have like a system that helps compensate people that you pay into, similar to insurance, I guess, but is covering things that actually make more sense. I don't know. I don't have all the answers by all means, but what I would say is that I do believe that the literature is becoming more and more definitive. There's never settled science. Don't let anybody ever tell you there's settled science. The whole point of science is to continually be questioning what we know and what we learn, and looking for something else that answers that question. And if something doesn't, make sense, or doesn't answer the question, or we kind of maybe not cast it aside completely, but we put it on the shelf for a later date. A lot of these metabolic treatments have been cast aside, 2-DGs and 3 bromopyruvates, and I don't know, metformin or statins or whatever it is, EGCGs, because it doesn't work in a vacuum. If I give EGCG and the cancer isn't completely miraculously gone, that means it's not effective. That's probably not true either. It just means that it maybe needs to be looked at from a different perspective and maybe added to like a combination protocol. Anyway, I'm gonna completely get. I'm off track, but I use this paper to get myself off track because I think that it highlights, the elephant in the room, what a lot of us know in our hearts already, and we're seeing in front of us with our eyes, but we're being kind of continually gaslit by the system that the only way to treat cancer is chemotherapy, radiation, and surgery, when that's probably a very untrue statement. Although, it's not well established within the system. What I'll say is that I have quite a lot of slides left talking about PFK, at least a good, let me see here, at least 15 more slides. And it's probably the 15 slides that are the most high yield for us, because it's looking at specific things that can, inhibit and or downregulate PFK. And I always say that for last because I want you guys to understand why we're looking at this particular target and its importance in a vacuum, right? Like they're looking at PFK-P and PFK-L kind of in a vacuum. They're saying, okay, if this enzyme is upregulated and expressed, it has this effect on the Warburg effect, and it has this effect on patient survival, right? So if this one enzyme is that important, imagine what the entire system of aerobic glycolysis and how important that is. So what I would say is that although we're looking at each one of these things in a vacuum and we're doing that for a very particular purpose, this is not happening in a vacuum. And so therefore, it's the entire system that we're trying to dismantle by taking one piece of it at a time apart. And the same would be for hexokinase or for glucose transporters or lactate dehydrogenase or other things. You'll see when we go through this system, one step at a time, we'll see that each one of these steps is critically important, and it's critically important for the next step and the next step and the next step. And without, 11 steps, I think you're not going to make lactate. And if you're not going to make lactate, then the tumor microenvironment collapses. And then all of a sudden your immune system turns on and chemotherapy works and immunotherapy works better. And so you'll see that this is an entire system we're trying to dismantle, but we're doing it from a very systematic perspective in a very mechanistic way without getting completely off track or confused. So I hope it's been helpful going through it in this systematic fashion. It definitely helps me. If you think I'm disorganized, imagine what I would be if I didn't have these slides keeping me on track and keeping me in a methodical way of looking at this problem. Let me take a look at some of these slides. David says, thank you for your work. You're very welcome. I'm happy to be doing this. I don't know if I'd call this work. It doesn't feel like work. It feels like in some ways it feels like fun, but I know we're dealing with a not a very fun condition, which is cancer. Because I really love learning and I love being able to share all of this, information that other people, not me, have discovered, and I'm able to bring it to you. Hey, Dr. Casey, found your channel a few weeks ago. Really enjoyed and appreciate your work. Since most electrolyte powders are bound to citrate and malate, do you have a different suggestion? So, Kevin, I would say that I am still not willing to say that, giving either electrolytes or creatines or whatever that's bound to citrate or malate is a good idea. I have evidence to the contrary, right? Like we have that paper. Where the heck was it? I think it was this one. Yeah, I think this is it. The citrate strategy, right? They were using high doses of citrate to inhibit PFK, right? Which basically shut down to some degree the Warburg effect, and it shut down cancer metabolism, and it showed benefit, right? It showed, at least in these mice models, it was showing inhibiting the progression of a variety of different cancers, right? Sarcomas, pancreatic cancer, breast cancer, lung cancer, etc. This is very promising. Okay, it makes me less bearish on citrate than I was before, but knowing that citrate is what's used by the metabolism of glutamine, to make new fatty acids, I still have a hard time being like bullish on citrate, right? Like I'd have to have more data. I would say for now, me personally, I would avoid. If it was me and I had a choice to pick a magnesium that was a citrate or like a chloride or something like that, I would say probably not going to give magnesium citrate. Even though I like magnesium citrate, it's a fantastic for constipation. If anybody's constipated, we give it in the hospital. We give bottles of magnesium citrate, and it's very powerful. But in the context of cancer, I think the jury is still out. I think it's possibly harmful and possibly helpful. And I don't know. This is a definitive answer. So I would say probably avoid until we know a better definitive answer. Knowing what you do, if you had cancer, what protocol for oxidative stress, hyperbaric oxygen therapy would you lean towards, i.e. 90 minutes 3 days a week, 2.2 atmosphere, or 60 minutes 5 days a week? I want to talk about all of that, okay? And I'm going to have specific videos on HBOT, specific videos on IV vitamin C, its mechanisms, how it works, what the proposed protocols, may be. I would say that we don't know the answer completely to that. I would say that I have talked to via correspondence and email a very prominent professor who knows about HBOT probably more than anybody. And he told me that he doesn't recommend doing HBOT every day, for example. He recommends having a day in between, no matter what the atmosphere is. Definitely the higher the atmosphere, the ideal was like 2.5 atmosphere. And I've seen somewhere between 60 and 90 minutes for that being ideal. Not everybody has access to a hard shell chamber, which is what's required to get that level of pressure. And so a lot of people have access to soft shell chambers that are like as low as like 1.3 atmosphere, upwards of like 2 atmosphere. I've seen some soft shell chambers that are kind of like reinforced or something like that have the ability to go up to 2 atmosphere. In those cases, what I've been told, and this is like empiric treatment, is that if it's a lower atmosphere, we need to do it for longer periods of time and more frequent, but still not every day. But I still think that we're not sure. Good evening, Paul. Since the latest paper from Seafried didn't give us any protocol ideas about HBOT, yes, even though it didn't give any ideas about protocol ideas about HBOT in the most recent ketogenic metabolic paper, it doesn't mean there's not information from Seafried and or Dom D'Agostino about that. And so the information is there. It's just not in that paper. And that's what I'm kind of quoting when I'm kind of talking about this in a more general fashion. Thanks, Paul, for the support. Among the food and plants that block glutamine, do we already know which one is the most effective, please? Well, I would refer you back to, I have an entire series on glutamine inhibitors, both natural and drug. I would say that from a drug perspective, the most effective glutamine inhibitor, and it's kind of a misnomer because there's multiple targets of glutamine inhibition. We can block its uptake. We can block its utilization at multiple steps, including glutaminase and glutamine dehydrogenase. So therefore, I guess when we talk about glutamine inhibitors, colloquially, I guess we would mean glutaminase inhibitors because Dr. Seafried always talks about DON. And so DON is the prototypic glutaminase inhibitor. It may have other targets as well, but I don't know if that's like, I haven't seen like data that like decreases uptake or glutamine dehydrogenase or other things, but it definitely blocks glutaminase. I did a video not too long ago, maybe a couple months ago, on the use of betulinic acid. And it was promising because in those studies, it showed that betulinic acid, there were a couple other things too that were much harder to obtain, but betulinic acid was actually more effective at lower concentrations at blocking the glutaminase enzyme than DON is. The issue with a lot of these inhibitors, and that's universal, is that because they're not drugs, they can have poor absorption into the body, right? And or they require an oral amount that would be so high in terms of like dose that it would be very difficult to take in, right? So my point is that there are a lot of things that block glutamine. I have a whole series on it. And I'm, again, methodical about the way I handle it, whether I'm talking about glutamine inhibition at SLC1A5 or SLC7A11, or I'm talking about glutaminase, or I'm talking about glutamine dehydrogenase. I talk about all those things, and I have a variety of videos on those. But what I would say is that the issue is absorption. So that's where I think that, we know pharmacologically that, I don't know, let's say EGCG blocks glutamine dehydrogenase, or quercetin blocks glutamine dehydrogenase, or I don't know, curcumin or berberine blocks glutaminase, or betulinic acid blocks glutaminase. These are all plant-based medicines, right? We need industry to give us probably either really highly effective liposomal formulations, maybe, or we need intravenous formulations. And I'm telling you that, even though I don't have a clinic, so I don't do these things personally, because I am in contact with so many people in the alternative cancer space, clients and the like, there are intravenous curcumins, there are intravenous quercetins, there are intravenous EGCGs, I don't know of intravenous betulinic acid. But my point is that there are formulations that are intravenous that are being used. The issue is, how much are they're charging people? Are you getting the right dose? Like, what's the frequency? So there's just a lot to work out with these things. We have proof of concept of dozens of things. It's just that we don't have the next levels of study, which will require study. We don't know a lot of these things. That's why, just a very example would be like Fenben versus Menben. It's not that Fenben isn't probably the same medication. Fenben doesn't do the exact same thing. It's just that we have human data on dosing, on frequency, on, et cetera, on menbendazole versus Fenben. So it's like, obviously that would be the best medication to use if it's available to a patient, right? So it's going to be the same for some of these other things. What about pairing it with DMSO? So the issue with DMSO is, my concern is that it's a sulfur-based compound, and sulfur is used by a lot of what they call thiol-based antioxidant systems. That's like the pyridoxins, the thioredoxins, the glutathione systems, et cetera. And I would be concerned potentially about DMSO, as well as MSM and other things, enhancing that for patients. And therefore, I think it has to be scrutinized. Will DMSO ultimately be the magic bullet that they have tried to make it seem like been for the last 30 years? Maybe. I'm not against it completely. I want to be careful with it. You hear about coffee enemas in regards to cancer. I don't know if that's a question. Maybe it's a statement. Curious what your thoughts are. Does it increase glutathione in the way that it would be against metabolic therapy? Yeah. So I used to be a vegan years ago for about 2-year periods. I was a raw vegan even for a period of time. And when you're in that kind of environment, you'll hear about a lot of therapies. And one of the therapies that is talked about, raw vegans talk about a lot, is the Gerson therapy. And the Gerson therapy is basically giving high amounts of juices, mostly carrot juice with a little bit of green apple, and some other vegetable juices, as well as like I forgot what they call the soup, but it's like a cancer soup. I mean, I've made it dozens of times when I was a vegan. And then the other part of the therapy is like several coffee enemas throughout the day. And the reason why, at least they're using it for those therapies, is, again, I'm speculating based off what they believe, is that they believe that doing coffee enemas allow the caffeine to bypass first pass metabolism and get in through the rectal plexus, like the rectal vessels, and allow it to go straight to the liver and dump toxins through the gallbladder and through the liver system. And it's mostly as a way to detoxify. I don't believe that their goal with it is to increase glutathione. I'd have to look, whether or not glutathione is either enhanced or inhibited by caffeine or some of the other coffee compounds. I don't know enough about that. So therefore, I don't know the answer to your question. It may have an effect on glutathione, but I don't believe that that's what they're doing. I think they're trying to allow the coffee to allow the liver to dump toxins into the small intestine. Again, that's their goal. That's what they talk about. If there's a more, I don't want to say scientific. That's derogatory. But if there's a more worked out mechanism of how it works, I would be interested in reading it. I don't know. I don't know if I would recommend that. To be honest with you, I would consider Laetrile up to 9 gram infusions paired with pancreatic enzymes. Yeah. Laetrile is, look, I've been involved in integrative medicine even before I was in medical school, honestly. So we're talking like now, I guess now 20 years. And since I read the book, what was the book that it was by, I don't know, I'm blanking on the name, probably because I'm a little bit tired. It's Friday. I'm on day 5 of 7 of my hospital this week, and I'm here with you guys. I'm a little bit scatterbrained, but my point is that I've heard about Laetrile for 20 years. And before I understood, the metabolism of cancer, I took it at face value. Probably helps, right? But when I looked at the mechanism, and I'm willing to relook at the updated, literature or mechanisms or papers or, even discussions about Laetrile, it didn't make sense to me. And I have not seen or heard of people like being miraculously like cured by it. So again, it could be one of those things like it by itself doesn't work, but maybe in combination with other things, it works. I don't know why pancreatic enzymes would work. I'll be very honest with you. It doesn't mean that it doesn't work, or it doesn't mean it can't work. It just means I don't understand how it would help you. And I think that people get pushed into these things because you can literally find a paper on just about anything that, I don't know, coffee destroys cancer, through activating something. And I think I always, even though maybe it doesn't seem like it, I always try to refocus us and orient us back to the true north, which is glucose, glutamine, okay? Because that's the gasoline that cancer needs, right? So I always look at something through the lens of, okay, yes, this compound X has an effect on cancer in a test tube or in a rat or maybe even a human, who knows? But does it fundamentally have an effect on glucose or glutamine? Yes or no? No? Okay. It could be helpful in the future on the side as an adjunct somehow, right? But I'm going to refocus us back on what do we know affects glucose and glutamine, because that is how cancer fundamentally works. Even if RAS or MYC or HIF1 alpha, if those are upregulated, it all works through glucose and glutamine. And that's how the thing survives, right? Through substrate level phosphorylation or the Warburg effect, or however you want to call it. So therefore, I don't see how pancreatic enzymes or Laetrile is going to affect that. So therefore, it doesn't mean it's not completely effective or it doesn't have promise or a role somewhere, but it's just not going to be like the top 10 things that I would recommend to a patient, because it doesn't, at least from what I understand, do that. They help break down the coating layer around cancer cells. I know they talk about this. Look, I've seen these things for years, and what they propose. Yeah, I don't want to say it seems like pseudoscience. But it does. It feels like that, and it has felt like that. If you want me to be very frank with you, since the first time I heard about it when I was in college, and I think it's possible. It just seems it seems unlikely, and I just don't want people putting a lot of hope and faith into those things that don't make as much sense, and not refocusing on things that do make a ton of sense. But that being said, I don't have all the answers. C-Free doesn't have all the answers. No one has all the answers. If someone had all the answers, they'd be probably very famous and or dead, and there would be no cancer. So I don't want to pretend like I have all the answers. It's just that from what I understand, one person's understanding of cancer metabolism and cell biology and biochemistry and medicine, because I'm also a doctor, I would also say that it just doesn't make sense to me. If I get enough data that makes me convinced, I will believe it. Okay, because I want to be open-minded always, because I criticize the mainstream establishment for not being open-minded, and I don't want to be that same way, looking at this perspective also. But I don't know. If you send me papers via email that can convince me, I will read them, and I will give my updated opinion on it. But as of right now, I'm pretty, I don't want to say negative. I just don't know if I would think that would be like a top thing I would do. Okay. Look, I've got an hour and 20 minutes, most of this rambling on. It's definitely Friday. It's definitely day 5 of 7 of my hospital this week. I have a 12-hour shift I have to do later tonight. So I'm happy to be with you all. I hope that this is very helpful for someone in the audience. I hope you have a nice weekend too, Sylvia. I'll be at the hospital. I'll be working. We work 7 days on, 7 days off. So this is my week on. But, I hope that this information, in particular phosphofructokinase, or the last couple of videos on glucose metabolism through glucose transporters or hexokinase, I hope this is interesting information, but I hope it's helpful information to you. And I hope it's encouraging information to you as well, because one of the things that I think that we get subject to within oncology is that there's nothing I can do about this. I'm just a victim, and there's nothing I can do. And I think that there's one thing that we can see from this series is that we have a lot of power over our body's systems, and we have a lot of tools in our tool bag. Some of those tools are difficult to obtain and expensive, like IV vitamin C or HBOT or whatever. Some things are not expensive at all. Some things are free. Fasting is free, right? So some things are not expensive at all. But if nothing else, I think we understand that we have a lot of tools in our tool bag. And if you have anybody in your life who needs encouragement, needs perspective, and needs tools in their tool bag, please share it with them. And until next time.